your convenience, this video will be divided into chapters using the timestamps that are given in the video description. And the subject of this video is how to use GeoGebra to identify the components of a bivector. What do I mean by that term? Well, there are times when we want to express a given bivector as a linear combination of the unit bivectors, and I'm working here in Geometric Algebra dimension 3. So we can express any given bivector as the sum of some scalar times a bivector e1, e2, plus some other scalar times the unit bivector e2, e3, plus some third scalar times the unit bivector e3, e1. So I have to give a brief plug here for GeoGebra. It's fantastic for just about anything in math that involves geometry in any way, and I'll put the link in the video description. It's free, and it's wonderful for checking solutions that we derive via three-dimensional geometric algebra, because many of our solutions can be expressed in terms of projections, rotations, rejections, etc., which we can construct easily using GeoGebra's built-in tools. So we can check solutions without having to resort to coordinates and such. In cases where we do want to use coordinates, GeoGebra can quite readily give us the components of vectors, but it does not, to my knowledge, have a built-in tool for giving components of bivectors. So we have to do that ourselves. And we'll give a numerical example at the end of this video. So how do we do this? Well, we use the dual relationship. And we know from geometric algebra that if we multiply any bivector, and I'm using a unit bivector here for simplicity, by the inverse of the unit trivector for three-dimensional geometric algebra, what we get is a unit vector that is perpendicular to that bivector. So if we multiply both sides here by I3 itself, we get that b hat is equal to the unit vector v hat times I3. And if we expand that out, starting by expressing v hat in this way, if we work all this out here, we come to this expression. And I have a separate video which I'll link up at the right-hand upper corner here to show how to simplify some of these expressions for those of you who are new to geometric algebra. So when the smoke clears here, we get v1 times this unit bivector and such and so on. If we want to put that in the order e1, e2, e2, e3, then e3, e1, this is what we get. So we can identify this coefficient here, b12 would be v3 of the unit vector rather. b23 would be the v1 of the unit vector, and b31 is v2 of the unit vector. So let's do one for real here. This will be our numerical example. We're going to start out here with our axes parallel to GeoGebra's own axes, and then we're going to fiddle around with this and move and change our reference frame a little bit, because very many times that's what we want to do to check with or when we want to check our solutions, find out whether we've lucked out and everything just lines up because we use GeoGebra's built-in reference system. So we roll our own here and then transform it to see whether everything still works. So the first thing we have to do here is construct a unit vector that is perpendicular to the bivector. So I'll do that quickly here. We'll choose some point on this plane, construct a line perpendicular to that plane and through that point, and I'll just choose some other point here and construct a vector there from that point to there. And that vector, what is its name? U. Okay, now what I have to do is construct a unit vector in that same direction. And you'll notice here I'm using the right-hand convention. This is the direction of our unit bivector, so that's the direction of our unit vector. So what do I do now? Well, I need to show some equations here. I'm going to say that I'm going to have to write here a little bit. I'm going to call this unit vector v hat. V hat is equal to the command unit vector of u, which is a vector that I just constructed up here. And here's our unit vector that I just made. Now to clarify things a little bit, I'm going to hide that vector, and so this is our unit vector that we've constructed. Now, again, from what we saw just a moment ago, and I'll put that back here, we have this correspondence. V3 is B12, V1 is B23, V2 is B31. I'll write this now. Now, the dot, we can find the V1s, V2, and V3 according to our reference system by using the dot products. So V1 is V hat dot E1, and you can read the rest here. So our B12 is V3, so I'll just write here exactly what, or I'll type in exactly what I have here. B12 is equal to V hat times, the times in GeoGebra when we're using vectors is the dot product, E3. Next, B23 is equal to V hat times E1. And B31 is equal to V hat times E2. B31 equal V hat times E2. So, if I've done all this correctly, this should all work here, and we get, oh, look at that. Our coefficients are all equal. Now, does that make sense? Well, yes, because if we look here, our plane cuts the given axes, or the axes of GeoGebra, at equal distances. So, yeah, this bivector b hat, or the weights here, the coefficients of the three unit bivectors should all be equal. Well, that's great. Let's see now what happens if we play around with this a little bit. They change. And in fact, what I'm going to do here is make E2 parallel to this line of intersection. Now, when that happens, b hat should be the sum of just, or some weighted sum of just these two bivectors here. This one's perpendicular to that plane, so it shouldn't contribute anything. And you can see that the E3, E1 coefficient is indeed very nearly equal to 0. What if we play around with that a little bit differently? Now I'm going to make it like this. So now the E1, E2 bivector is perpendicular to b hat, so its coefficient should be very nearly equal to 0. So, and that's confirmed. So this all works out. It comes out very nicely and very simply. Again, GeoGebra is a wonderful tool, and for those who aren't familiar with it, for gosh sakes, please go check it out. I hope you'll consider also joining the LinkedIn group Pre-University Geometric Algebra, which devotes itself to preparing resources like these. And thank you for your time.